Howdy, howdy. This is Mr. Potter. We're continuing a discussion about related rates. And so there's a couple of other standard problems that we see a lot when we're talking about these related rates. And I'd be remiss if I didn't start by talking about the Lamppost problem. So here's an example situation. I've got a man that's 6 foot tall. He's walking away from a 15-foot tall lamppost at a rate of 5 feet per second. And when he's 10 feet away from the base of the light, the question is, how fast is the length of his shadow changing? So imagine I've got a lamppost. I've got a man, and the light from this lamppost is going to hit the top of the man's head and create a shadow on the ground. Now, what I know from this problem is that my lamppost is 15 feet tall, and this actually is a constant, as is the man's 6 foot tall height. That's constant. But this distance here, right now, it's 10 feet. But keep in mind that it's changing. dx dt is 5 feet. And my question is, I want to find out how long is the length of the shadow changing. So, looking at what I've got here, I really do have two triangles. I've got one triangle that represents the man and his shadow. And for this man and his shadow, the man is 6 feet tall, and his shadow is s feet tall. But I also have another triangle over here, which is dealing with the top of the light post to the top of the man's head, and the distance that the man is from the lamp post. Well, this is 15 minus 6, which is 9 feet tall. And the distance from the lamp post to the man is x. And at this exact moment, it's 10 feet. But it's a changing distance, so I don't want to treat it as a constant. So I've got 6 and s. And I've got 9 and x. And these triangles are both right triangles because they share this right angle. And these angles here have to be the same, as do these angles here. So what I really have are similar triangles. And because I'm dealing with similar triangles, I know that their sides are proportional. So 6 over s equals 9 over x. So I have a relationship between s and x. I know that s is equal to 2/3 of x. And from this relationship, this is step 1. I've come up with a model. I've come up with some type of description that involves the length of the shadow to the distance that the person is walking. And that's always my first step, is to come up with some type of relationship, some type of model that relates the two variables we're talking about. The second thing that I need to do is take the derivative with respect to time. So I'm going to have ds dt. The length of the shadow changing over time is equal to 2/3 times dx dt, how fast the man is walking with respect to time. And that's the quantity that I know. I know that is 5 feet per second. So this is going to be equal to 2/3 of 5, which would really be 10/3. So this is my solution. Recall that I really want to deal with the answer. I want to answer this question: how fast is the length of the shadow changing? And I could say that the length of the shadow is increasing at 10/3 feet per second. So notice I've got here is my answer. This answer answers the question. 10/3 just happened to be the solution to the equation that I had. But I need to make sure that I always answer the question. Now, this is one way that the lamppost problem can be posed, but it's also seen another way. So this is walking away from a lamppost too. So I've got the exact same situation. I have the 15-foot tall lamppost. I've got the 6-foot tall man. I've got the light coming from the lamppost, making a shadow on the ground. And this is 15 feet. This is 6 feet. This distance right now is 10, but it's changing at 5 feet per second. But the question is, how fast is the tip of the shadow moving? So in reality, I need to deal with this quantity here. This is where the tip of my shadow is. And I'm using a capital T. I don't the confusion when I take the derivative with respect to time, when I take the derivative to a lowercase t. So just as before, I had two situations. I have this triangle here, which represents x, the distance from the lamppost, and 9, the distance from the person's head vertically to the top of the lamppost. So I'm going to have two similar triangles, just as I did before. One with 9 and x. But this time, since I'm talking about the tip of the shadow, it's really the tip of this whole triangle here. And so the whole triangle has a height of 15 and a base of capital T. So because again these triangles are similar, these angles in particular are the same as is the right angle down here, these sides are proportional. So I have 9 over x equals 15 over t. And so I can find a relationship for t in terms of x. T is equal to 15 ninths of x, which would really be 5/3 of x. And this is my model. Remember, step 1's always coming up with a model that relates the two variables here. Here my variables are 1, how he's walking away from the light post, and 2, where the tip of the shadow is in relation to the light post. And so now I want to take the derivative with respect to time, so I'm looking for the change in the tip with respect to time, and that's going to be equal to 5/3 times the change in x with respect to time, which we know that quantity is 5. And so I've got 5/3 of 5, which would be 25/3. Now again, remember that this is a solution, and what I'm looking for is an answer. So I need to make sure that I answer the question. The question is, how fast is the tip of the shadow moving? So I need to write the tip of the shadow is moving at 25/3 feet per second. And it should make sense to us that what's happening is he's walking a certain distance, his shadow is growing at a certain distance, and so this tip ends up moving at a certain speed. In other words, this dt dt is really equal to dx dt that we were given plus the ds dt that we found in the previous problem. So I could have used another relationship. I could have said that the tip of my shadow is really equal to the distance plus the length of the shadow. In other words, t is really equal to x plus s, this distance here, which we found in the previous problem. But we would have had to work that problem first. And so I could have done it either without that previous information or with this previous information. The idea that 25 thirds is really the sum of 5 plus 10 thirds. So I could have gotten my answer that way as well. The Lamppost problem is one of the problems that every calculus student sees, every calculus student has to approach. The key thing, though, is that we're still looking